Howdy, my name is A. Ray Moody. This is my Lab 3 beam vibration going over the static and dynamic behavior of a cantilever beam. Outline, the laboratory objective, experimental setup, and experimental results, talking both about the static and dynamic displacement measurements, and then a general overview of the vibration controls and a summary of that data, and then finally conclusion, and then a reference. Laboratory objectives to measure displacement response of cantilever beam using a Wheatstone bridge. Model cantilever beam as an equivalent spring mass damper system. Perform spectral analysis on measured displacement data to find the beam's natural frequency. Cantilever beam was, so for the setup, a cantilever beam was created by clamping an aluminum ruler to a bench as shown in the picture on the left. A strain gauge on a ruler was then wired to a Wheatstone bridge as shown in the picture on the right, connected to an MSP432. A second ruler was clamped to the table to act as a reference plane when taking displacement measurements. All static tests used Nichols standard loads varying from 10 grams to 50 grams is placed at the far end of the cantilever beam. Tip displacement was then measured with another ruler as shown below, the MSP432, to log the voltage from the Wheatstone bridge. So for further experimental setup, once the data was collected, an equation was formed relating displacement to the voltage measured on the Wheatstone bridge. From there, 4 dynamic cases were then studied. Case 1, tip was held down 15 millimeters and released at t equals 0. Case 2, a quoit was dropped on the far end of the beam, imparting an initial velocity at the far end. Case 3, the same as case 1, however, blue tape was put on the bottom of the ruler for about 2 inches of it to add damping, and case 4 is the same as case 3. However, it used a clear double-sided tape instead of a blue tape. To first find strain gauge sensitivity, the measured displacements was then related to the tip load and the average voltage of the Wheatstone bridge. Strain gauge sensitivity was used to determine the average change in voltage against the tip, and a measurement of about 4,200 millimeters a volt was found, and that was created by the slope of the line of best fit. So to find the spring constant, the force and displacement were graphed against each other, and the slope of that line of best fit was used as the K. Assumptions made was that the local gravity was 9.81 meters a second squared, and the line of best fit had an x-intercept at 0, 0. So for the initial displacement, the beam was held down about 15 millimeters and then rapidly released. The bottom right shows the data gained from that measurement. As shown, it is clearly an underdamped system. The system's parameters were then estimated by first finding the damp natural frequency by finding the time between peaks. And then once that was found, a damping ratio was found by a line of best, or a equation fit using MATLAB. And a damping ratio of about 0.7 was found, so it's underdamped. And below shows how the calculated values. So a spring mass system was then modeled using the following equation from the previous data that we collected, orange being the equivalent spring mass and black being the actual data observed. And then a spectrum analysis was performed to see what frequencies the system was vibrating at. As shown, there's a peak at around 14 hertz, which did match our damped natural frequency from before. So for the initial velocity at the far end, a coin was dropped at the far end, as shown in the bottom right, and then the data collected is shown on the top right graph. And then another spectrum analysis was shown, or was calculated. There seems to be much more of an initial peak in oscillation, like around 1, and then another around 14, where 14 again is the natural frequency calculated. And it seems to be so after that, case 3 and 4 were performed using a small 2-inch length of tape applied to the underside of the beam. Case 3 was blue duct tape, and case 4 was clear double-sided tape. Below shows the damping ratio for case 1, no tape, case 3, tape 1, and case 4, tape 2, where no tape and tape 2 are pretty similar, but the blue tape clearly actually increased the damping coefficient. Below is combined data from all 4 cases, case 1, 2, 3, and 4. All cases are underdamped. However, there is little variation in frequency between cases. However, case 3, the one with the blue tape, clearly has a larger damping ratio than any of the other cases. Conclusion, the type of tape can dramatically change the effect of dampening. There's no major difference between the internal displacement and initial impulse, or there's no major difference between initial displacement and initial impulse, although initial impulse did seem to impart more frequencies into the beam. And the spring block system lacks the ability to model a cantilever in anything other than the first harmonic, because it didn't really model any of the variation that we saw, especially when compared to the initial impulse. And that is my reference.